Okay, folks, let's talk today about glaciers and deserts. Go to some of the extremes on Earth's surface, go to some of the coldest places and some of the driest places. First, we'll talk about how glaciers actually form and that process, how it works, and we'll differentiate mountain from continental glaciers. That's an important distinction because they create very different features. They work on very different scales. We'll talk about glacial landforms, and we'll tie that back into this distinction. And then we'll talk briefly about glacial cycles and climate change over Earth's long history. So this is not necessarily bringing into any anthropogenic human-caused effects yet, but we'll talk about sort of the natural glacial cycles that go on a little bit. And then lastly, we'll cover deserts briefly in one sub-lecture. So glaciers form from snow. Snow falling on upland areas, if it accumulates, can form glacial ice. So it works a lot like compaction and cementation of other cement or of other sedimentary rocks. And some folks might even consider glaciers to be a type of sedimentary rock made out of chemical sediments, because these snow flakes are going to settle onto the surface. Over time, they're going to get compressed and they're going to reconfigure themselves as water molecules exchange between some of these, and they will become granular ice with less pore space, 50% air instead. And then as you compress it a little bit more, it's called firn, and now it's down to 20 to 30% air. And eventually you compress it enough where it would be considered glacial ice. If you were to drill down through any particular glacier, this is the order that you'd find things. You'd find some snow on top, you'd find granular ice and firn below it, and then in the core of that glacier, you'd find the actual glacial ice, which is stored some of that air as bubbles. So that's sort of small picture locally, the fact that glaciers form because snow accumulates on surfaces and turns to ice. But if we look at the morphology of a particular glacier, this one here, right, we see that in some places, the snow is accumulating over time, which means that ice is being added to the glacier in some areas, and in other areas, ablation or removal of that snow dominates. And that can happen either via melting, so solid going to liquid, or what we call sublimation. This is just solid goes straight to the gas phase. So both of those can happen. If you look at a particular glacier overall, we could have a situation where the accumulation, the addition, is less than the ablation, the subtraction. And if that's the case, then your ice is going to decrease over time. You can have them be equal, or you can have the accumulation be greater. Now, the one other thing that we need to add in are these arrows here. This is key because it turns out that glaciers themselves, the ice, solid ice itself, actually flows slowly, much like a river would flow downhill, only at much slower speeds. And that ice flows from areas where accumulation dominates to areas where ablation dominates. So it will flow from upland areas where the accumulation tends to happen to downward areas where the ablation tends to happen. If you are in a situation where the accumulation is less than the ablation, right? So you're net subtracting from the glacier, the place that actually loses the ice first is from the ice front here. If accumulation is less, the ice front actually recedes and the glacier shrinks backward toward where it's accumulating. If they're equal, the glacier overall stays roughly where it is, although you still have this sort of conveyor belt motion of the ice moving down slope. And if accumulation dominates over ablation, then this ice front will actually move forward, outward, away from where it's actually growing. That's interesting because, right, this ice isn't being added to in this area. The ice is actually being added to much further up slope, but it's still growing in this direction, even though ablation is dominant in this area because of that flow of the ice down slope. Much like a river, a glacier flows, and we mentioned that, and much like a river, the glacier will flow at different speeds in different spots. So if one were to drive a set of stakes here deep into the glacier and then come back sometime later, The stakes in the center here, you would notice, would have moved farther. That's because the center of the ice, away from the sides of the glacier, actually moves faster. So center and top of the glacier, that ice moves faster than on the sides and on the bottom. That should remind you of this velocity profile that we've seen in streams, right? Where the center and top moves faster than the water near the sides and the bottom. Same sort of thing happens in glaciers, and it's for the same reasons, that there's drag, friction, being forces exerting themselves on the ice as it flows, which slows the ice down near where that friction is happening at the edges. So that's the basics of how they form. Snow adds to glaciers, the glaciers flow in a particular spot, and then the balance is going to control whether they grow or shrink over time. Now let's talk about something a little different, which is the distinction between mountain glaciers, which are small, relatively speaking, and continental glaciers, which cover, as you might expect, whole continents or large parts of continents. So these are very large. And we have two examples here. So a mountain glacier might look something like this, filling one mountain valley or a network of mountain valleys. At any rate, they spread from high elevations, right, upslope, places higher in the mountains, and they're relatively small. And they're often confined to single valleys like this one. In contrast, continental glaciers, like the Antarctic continental glacier that we have on Earth's surface right now, they don't spread from high elevations, they spread from high latitudes, that's places near the poles. So we have one in Antarctica, we have one in Greenland also right now. Those are the two continental glaciers that we have on Earth's surface at the moment. These are huge, and they also cover up the underlying topography, whereas mountain glaciers are working their way around mountains, right? They don't really cover up the fact that there's a mountain here. Continental glaciers can cover up whole systems of mountains and valleys, right? You have no idea what the topography is actually doing in this area because it's all covered by up to miles of ice. So very thick as well, right? This is maybe tens of feet thick. These continental glaciers can be miles thick. So in the continental glaciers, those are the big ones, the ones that cover whole continents, the ice is going to move down and out from the thickest section. So this is sort of a cutaway image showing that, where the thickest ice is here, and it flows under the force of gravity, sort of trying to pull everything to the same elevation. It flows down and out away from that thickest area. And so it spreads outward from those thick areas. This is similar to, but not exactly the same as those mountain glaciers that move down from the highest elevations.